Welcome to the session on inverse Laplace transform. In this session, we shall discuss some inverses of Laplace transform. If Laplace transform of a function f of t is a function of s, that is, if L of f of t equal to f of s, then the inverse Laplace transform is defined as L inverse of f of s is equal to f of t. This is the definition of inverse Laplace transform. We have the elementary transformations. L of k is equal to k by s. Therefore, we can write L inverse of k by s is equal to k. Laplace transform of e raised to at is 1 by s minus a. Therefore, the inverse Laplace transform of 1 by s minus a is equal to e raised to at. Laplace transform of the trigonometric function sin at is a divided by s square plus a square. Therefore, L inverse of a divided by s square plus a square is sin at. Or we can write this as L inverse of 1 by s square plus a square as 1 by a into sin at. We have the Laplace transform of cos at. L of cos at is equal to s divided by s square plus a square. From this we can write L inverse of s divided by s square plus a square is equal to cos at. The Laplace transform of t raised to n is gamma n plus 1 divided by s raised to n plus 1. If n is an integer, we can write this as n factorial gamma n plus 1 is n factorial divided by s raised to n plus 1. Therefore, L inverse of 1 by s raised to n plus 1 can be written as t raised to n divided by gamma n plus 1, or if n is an integer, we can write this equal to t raised to n divided by n factorial. We have the Laplace transform of hyperbolic cosine cos h at as s divided by s square minus a square. Therefore, L inverse of s divided by s square minus a square is cos h at. Also, Laplace transform of sin h at, the hyperbolic sine, is a divided by s square minus a square. From this we can write L inverse of 1 by s square minus a square as 1 by a into sin h at. These are the elementary transformations and their inverses. Now we have the first shifting theorem for Laplace transform is if Laplace transform of a function f of t is equal to f of s, then the Laplace transform of the function multiplied by e raised to at is equal to f of s minus a. This is the first shifting theorem. Therefore, we can consider the inverse of this property, that is if L inverse of f of s is equal to f of t, then L inverse of f of s minus a is equal to e raised to at into f of t. Consider this function 1 by s minus a. We have to find inverse of this function. We have L inverse of 1 by s is equal to 1, because Laplace transform of 1 is 1 by s, therefore inverse of L inverse of 1 by s is 1. Here, instead of s in the given function, it is s minus a. Therefore, we can use this shifting property for inverse. This gives from this we can write L inverse of 1 by s minus a as 1 into e raised to at. That is e raised to at. Now we have to do some examples. First one is find the inverse Laplace transform of s square minus 3s plus 4. All divided by s cube. We had to find the inverse Laplace transform of this function. We can write this function as s square divided by s cube is 1 by s, minus 3 into s divided by s cube is minus 3 by s square, plus 4 divided by s cube. This is equal to L inverse of 1 by s minus L inverse of minus 3 into L inverse of 1 by s square plus 4 into L inverse of 1 by s cube. The linearity property of Laplace transform is applicable in the inverse Laplace transform also. Therefore, we have to write this as 3 terms, 3 inverse Laplace transform, 3 terms of inverses. This is equal to L inverse of 1 by s means 1 minus 3 into L inverse of 1 by s square is, we have L inverse of 1 by s raised to n plus 1 is equal to t raised to n divided by n factorial. Therefore, we can write L inverse of 1 by s square as t divided by 2 factorial. Here s square means s raised to 1 plus 1, that is n is equal to 1. Therefore, we can write this as t raised to 1 divided by 1 factorial. Sorry. plus 4 into here s cube, 3 means 2 plus 1. Here n is equal to 2 means t square divided by 2 factorial. 4 into t square divided by 2 factorial, which is equal to 1 minus 3 into t by 1 factorial means 1. Therefore, this term is minus 3 into t plus 2 factorial is 2. 4 by 2 means 2 t square. This is the required Laplace transform of this function. Consider this example. F of s is equal to s plus 2 divided by s square minus 4s plus 13. We have to find the inverse Laplace transform of this function. The given function can be written as s plus 2 divided by, in the denominator we have to make a perfect square. For this we add two square, that is 4 in the denominator, and we subtract the same in the denominator. We get s square minus 4s plus 4 minus 4 plus 13. We just add 4 and subtract the same in the denominator in order to make the denominator into a perfect square. This is equal to s plus 2 divided by, these three together will become s minus 2 whole square, plus it is here is 13 minus 4 means 9. This is equal to, now here s minus 2 the whole square plus 9 means, in the numerator s plus 2, the denominator s minus 2 whole square is the first term, plus 9 means 3 square. Now we have to make s minus 2 in the numerator. We write the numerator as s minus 2 plus 2 plus 2. That is, we just add 2 and subtract the same in the numerator, all divided by s minus 2 whole square plus 3 square. This is equal to s minus 2 plus 2 is 4 divided by s minus 2 the whole square plus 3 square. Now split into two terms, which is equal to s minus 2 divided by s minus 2 whole square plus 3 square plus 4 divided by s minus 2 the whole square plus 3 square. Now we can take the inverses because these two terms are in the standard form. Therefore, L inverse of s plus 2 divided by s square minus 4s plus 13 is equal to L inverse of s minus 2 divided by s minus 2 square plus 3 square plus 4 times L inverse of 1 by s minus 2 the whole square plus 3 square. This is equal to, we have L inverse of s by s square plus a square is cos 80. Here instead of s, it is s minus 2. Therefore, we have to use the first shifting property for the inverse. We can write this inverse as e raised to 2t into cos 3t, because L inverse of s by s square plus 3 square is cos 3t. Here instead of s, the terms are s minus 2 in the numerator, and in the denominator also it is s minus 2 instead of s. Therefore, we have to multiply cos 3t with e raised to 2t, because here s minus 2, therefore we multiply by e raised to 2t plus 4 into, similarly here 1 by, if 1 by s square plus 3 square, the inverse is 1 by 3 into sin 3t, because L inverse of 1 by s square plus a square is 1 by a sin 80. Here 3 square means L inverse of 1 by s square plus 3 square is equal to 1 by 3 into sin 3t. Here instead of s in this function, it is s minus 2, means we have to multiply 1 by 3 into sin 3t by e raised to 2t. Therefore, 4 into 1 by 3 into e raised to 2t into sin 3t. That is, the required inverse is e raised to 2t can be taken common into cos 3t plus 4 by 3 sin 3t. Now consider this function f of s is equal to 4s plus 15 divided by 16 square minus 25. We have to find inverse of this function. We write the given function as 4s plus 15 all divided by, here we have to take 16 outside, 16 into s square minus 25 divided by 16, because in the standard results the coefficients of s square are 1 in all the standard form. Therefore, we have to make the coefficient of s square 1. This is equal to, now we split into two terms, 4s divided by 16 into s square minus, here 25 by 16 means 5 by 4 square, 16 into s square minus 5 by 4 square in the denominator, plus here 15 by 16, sorry 15 by 16 s square minus 5 by 4 the whole square. This is equal to 4 by 16 means 1 by 4. Here s by s square minus 5 by 4 whole square, which is the, if we apply the inverses, we have to write this as L inverse of 4s plus 15 divided by 16 square minus 25 is equal to 4 by 16 into L inverse of s by s square minus 5 by 4 the whole square. That is 4 by 16 means 1 by 4 into L inverse of s by s square minus 5 by 4 the whole square, plus here 15 by 16 into L inverse of 1 by s square minus 5 by 4 the whole square. This is equal to 1 by 4 into L inverse of s by s square minus a square is cos hat. Therefore, here instead of 8 is 5 by 4. We can write inverse of this as the hyperbolic cos h at, here a is 5 by 4, cos h 5 by 4 t plus 15 by 16 into here L inverse of 1 by s square minus 5 by 4 the whole square. It is 1 by 5 by 4 into sin h 5 by 4 t. Which is equal to 1 by 4 into cos h 5 by 4 t plus, on simplification we get this as 3 by 4 into sin h 5 by 4 t. This is the required inverse. Now consider another function f of s equal to 2s square minus 4 divided by s plus 1 into s minus 2 into s minus 3. We have to find the inverse Laplace transform of this function. First of all, we have to use the partial fraction method in order to decompose this function. Let the given function 2s square minus 4 divided by s plus 1 into s minus 2 into s minus 3 is equal to a divided by s plus 1. Here all are linear factors. Therefore, we can write this fraction as a by s plus 1 plus b by s minus 2 plus c by s minus 3. Multiplying both sides by s plus 1 into s minus 2 into s minus 3, we get 2s square minus 4 is equal to a into, here if we multiply with product of this 3, s plus 1 and s plus 1 cancelled. The remaining terms are a into s minus 2 into s minus 3 plus b into, here s minus 2 cancelled, s plus 1 into s minus 3 plus c into s minus 3 will be cancelled, s plus 1 into s minus 2. Now put s is equal to 2. When s is equal to 2, we get 2 into 2 square is 2 square means 4, 4 into 2 is 8, 8 minus 4 is 4, which is equal to, here this first term and this third term will be 0 because there is a factor s minus 2 in both the terms. Therefore, the remaining terms are b into, when s equal to 2, 2 plus 1 is 3, into when s is equal to 2, 2 minus 3 is minus 1, which gives minus 1 into 3 into b means minus 3b is equal to 4, implies b is equal to 4 divided by minus 3. When s is equal to 3, we get 3 square into 2, that means 9 into 2 is 18, 18 minus 4 is 14, is equal to, this first term and the second term will become 0 because there is a factor s minus 3 in both the terms. The remaining term is c into, when s is equal to 3, s plus 1 means 4, into s minus 2 means 3 minus 2 is 1, which gives here 4, c equal to 14 means c equal to 14 divided by 4. That is 7 by 2. When s is equal to minus 1, we get minus 1 square into 2 is 1 into 2, that is 2. 2 minus 4 is minus 2, which is equal to, this second term and third term will become 0, and the remaining term is a into minus 1 minus 2 is minus 3 into minus 1 minus 3 is minus 4, which gives that is 4 into 3, minus 4 into minus 3 means 12. 12a is equal to minus 2, implies a is equal to minus 2 divided by 12, which is equal to minus 1 by 6. Therefore, the given function 2s square minus 4 divided by s plus 1 into s minus 2 into s minus 3 can be written as, this is equal to, here a is minus 1 by 6. Therefore, we have to substitute minus 1 by 6 here. Value of b is minus 4 by 3. And value of c is 7 by 2. Now, we can take the inverses. On both sides, we get L inverse of, that is the inverse Laplace transform of this function 2s square minus 4 divided by s plus 1 into s minus 2 into s minus 3 is equal to minus 1 by 6 into L inverse of 1 by s plus 1 minus 4 by 3 into L inverse of 1 by s minus 2 plus 7 by 2 into L inverse of 1 by s minus 3, which is equal to minus 1 by 6 into L inverse of 1 by s plus 1 is e raised to minus t minus 4 by 3 into L inverse of 1 by s minus 2 is e raised to 2t plus 7 by 2 into L inverse of 1 by s minus 3 is e raised to 3t. This is the required Laplace, inverse Laplace transform of the given function. Here we used the partial fraction method to find the inverses. With this example, we have to come to the end of this session. Hope that you have understood the inverse Laplace transform. Thank you for watching this class. Have a nice day.